Welcome to this lecture where we will discuss, we will continue from wherever we had stopped the last time. So, we were looking at density estimation techniques, specifically we looked at the maximum likelihood estimation techniques. Now, in today's class we will look at two other ways of estimating density functions. So, one is what is called as the Bayesian methods of estimation, of which maximum a posteriori probability estimate or a MAP estimate is one member. We will also look at non-parametric density estimates as a way to estimate the density functions. Now, recall that in maximum likelihood estimate, in ML estimate, the parameters theta, the parameter set, so which we were denoting with theta, is considered to be a deterministic variable. What does this mean? Now, our estimate on theta depended completely on the data that we had. So, recall the idea was to find theta such that it minimizes the KL divergence between the true density and the model density. However, as I said in the end of the last class, what happens is if you depend completely on data, especially when the cases in the cases when the data is very less in number, ML estimate may not be the best choice. So, we will also discuss, we will discuss this idea in detail when we look at the bias variance decomposition and the idea of overfitting and underfitting. Here is the example, right. So, when n is small, this number of data points are small, so ML estimate may not be optimal. Here is an example, right. So, as an example, consider, so ML estimate for a Bernoulli random variable. Okay, what is this? You remember what the ML estimate is? So, theta ML is simply equal to number of times the trial has yielded 1, if you consider divided by n, right. So, this is what the ML estimate is. Remember this is what our ML estimate was for a Bernoulli random variable. Now, suppose the data D is like this, we have like 1, 1, 1 and 0. This is what our data is. In this case, what the ML estimate is? It is 3 by 4. So, the question is this a good estimate, or maybe we can actually consider a more degenerative case where all 4 trials ended up in one of the outcomes. Okay. So, in this case the ML estimate is for that particular parameter is 1. So, now is this a good estimate is the question. Now, depends on what the underlying data is, okay, what the underlying reality is. Now, suppose our Bernoulli random variable that we have corresponds to a fair coin, which means that we, or rather we know that it is not the coin that has both sides as the same, but this ML estimate is telling you that the underlying random experiment that we are conducting has a coin that has both of its sides to be the same. Okay. Now, suppose we know the fact that this is not a coin with the same sides, both the same sides, how do we incorporate that knowledge that we have into the estimation technique is the question, right. So, let me write that. So, the above estimate is not optimal. So, So I am writing optimal within quotes because I have not defined what optimality is, in whatever sense. Let us say that you are looking at the difference between the estimate and the true estimate, okay, in an expected sense. So it is not an optimal, the above estimate is not optimal if the true value is around 0.5. This is just an example where ML estimate, especially if you have very less amount of samples, leads to bad estimates of the underlying parameter. Okay. Now the question is, how do you incorporate the belief that we already have regarding the parameter into our estimation technique is the question that we want to ask. So it is this question that the Bayesian estimates try to answer. Okay. So in Bayesian estimates, the idea is to incorporate the prior belief or information about the parameters. Now, if we already know that the underlying parameter has a particular type of form, it can only take this sort of value, then no matter what data tells us, we know that this is our belief and we want to incorporate our belief into the estimation technique. So now how do we do that mathematically is the question, and Bayesian ways gives you a way to incorporate that. Okay. Now in Bayesian methods, what is done is, mathematical way to do it is, assume the parameters theta to be a random variable and model the prior belief in its distribution. So far we have been looking at theta as a deterministic variable, right. So now assume that theta also is a random variable just like your data, and that has a distribution of itself. Now that distribution, okay, incorporates the belief that we already have regarding the parameters that we are trying to estimate. Okay. So this is the idea. Now in the example that we considered previously, suppose in the previous example of Bernoulli random variable, so you can assume, let us say, p theta of theta, which is a distribution on theta, right, write the equation later, to be having a distribution of this sort. So this is 0 and this is 1, okay, and this is p theta of theta. So let us say that this is around 0.5. Now this is a distribution that we assume on theta even before we look at data, right. Even before we look at our data, we assume that p theta has this distribution. So what is this actually saying? This is saying that I know that the value of theta being around 0.5 is the highest. Now given that I already know this, estimate my theta is the question that I am asking, no matter what my data say. Okay. Now if I only stop here, then I am completely oblivious to data. Even that is not a good idea, right. I mean, what if the coin that you have or the Bernoulli trials that you are conducting will skew your belief. Okay. This, and please remember that the prior belief that we have on the parameters is completely independent of data, and it only comes from sources that are not related to data. So that is why it is called a prior belief. Is that alright? So now if you have this sort of a distribution that is incorporated on the parameters, now you have to use this along with data to update your belief. Does it make sense? Yeah. Okay. So now let us see how to use this idea in estimation. The question is, doesn't that also introduce source of error? In what sense? Yeah, there is no way to know whether your belief is correct or not. So that's why it's called a belief, right? So use your belief. See, data can lie, okay, and your belief may be wrong. So you combine both of them. That's it. Now your estimation, of course, it will induce error in the sense that if you have wrong belief, then you end up getting wrong estimates. Okay. Now, yeah, you can't do anything about it. However, suppose your belief augments your data. The idea is to augment the observations with belief. So as you will see later, if you have infinite samples, then data will lead you to reality, right? Because if you conduct the random experiment large number of times, you know that law of large numbers takes into effect, and it will converge in probability. However, when you have small samples, data can lie, right, and belief can be wrong. So the question is, can we combine both of them in a meaningful manner? So now what is better is a different question. So we have not talked about how to quantify the betterness of an estimate. That's outside the scope of this particular course, but there are ways to do it. That's why you have this blue estimates and so on, right, where people talk of, suppose you have an estimate that you have gotten, how can you quantify the goodness of this estimate, and error bounds can be derived on top of them. Okay, can I bound the error that this particular estimator is giving and so on. What can be seen is that in the Bayesian methods, right, as you can probably guess, the error that is imposed or rather incorporated by imposing your belief is a function of your belief, obviously, right, but there is a way to incorporate your belief in the system. That's it. Okay, we will see later in the course, in a couple of classes, that this is exactly equivalent to the idea of regularization that people will do in the deterministic sense. We will see that in a while. Okay, so now how to incorporate this belief from an algorithmic standpoint is what we will see now. So suppose, so your data x is sampled from some px, right? This is our data that we have, and the parameters theta is coming from p theta, which is the prior on parameters. Okay. Now use Bayes' law to compute the posterior. So now note that theta parameters is also a random variable. Now we can talk of distributions, the posterior of the parameters given data, right. So posterior of parameters given data now is proportional to the prior on the parameters, and this is prior on the parameters is your belief, right, and this is the likelihood of data at a certain theta, right. You given a theta, you will get some likelihood. Okay, see, even in the maximum likelihood estimates, this makes sense. The only thing is, this is fixed at a particular point, and you take that it's a point estimate. Okay, in the Bayesian framework, this becomes an entire random variable. So the reason I wrote proportionality here is that we don't care about, we often don't care about the denominator, that is the normalization constant. You need this denominator to make it a proper density, but typically, at least in map kind of estimates, we don't care about the denominator. That's why I wrote it as proportional. This is Bayes' law. So this is how we use it. You start with, you incorporate your belief into p theta, and of course the likelihood is there, okay, which you have assumed. Multiply both of them and you get the posterior of the parameters given data. So now note that unlike in the case of the maximum likelihood estimate, where you get one particular point estimate for theta, here you get an entire distribution over theta. So basically the point is, initially you started with some belief, you assume that okay, my theta has this sort of a distribution. Now you observe data, then you update your belief. So this distribution over theta, see, posterior on theta given x is still a distribution over theta. So you start with an initial distribution over your parameters, and having observed your data, your belief on the parameters gets updated. Happens all the time in life, no? Right? Start with some belief, go to the real world, get whacked, and then update your belief. depending upon what your observations are. That is the idea. Now the question is, I mean, remember we are still considered we are still concerned about building a Bayes classifier. So now what do you do with an entire distribution over theta? We want one of it, no? There are ways to do it. One way to do it is pick the mode of this distribution and take that as your estimate for theta and move on. That is the map estimate. We'll write that in a while. Okay, is this idea clear? Start with a distribution over theta, okay, and get an updated distribution over theta by looking at your data. That's how you do it.
Sometimes we generally have a belief over the latent variable we talked about earlier, and we won't generally have the distribution over theta.
In the Bayesian methods, right, the belief typically the belief is over the parameters, not over latent variables, but there are methods which incorporate belief over latent variables as well, okay, which we will see later, but for now the belief is over theta. That is why I gave you that example of Bernoulli random variable, where you know, see what sort of belief can you have when you have a Bernoulli random variable. It is that, okay, the coin that I am tossing does not have both the sides as head. So that is one sort of belief. The other thing can be, okay, it's, see, maybe you can weigh it. See, how do you derive belief, right? That comes from the physics of the problem oftentimes. So let us say that you are looking at that coin, no? You weigh it for instance, and you know that one side is, let us say, 70% heavier than the other side. Okay, then you construct a belief according to that and then you incorporate it. That is how you do it. So belief is mostly on parameters for now. Okay, so later you can incorporate beliefs on other parts of the function as well, but right now it is on parameters. Okay. Okay, so now let us look at how to do it. So let us consider the example of, okay, so you compute this, or maybe I will write that, no. So how to use p theta of p theta given x. So one way to do it is using the map estimate, where take the mode of p theta given x as the estimate. This is called the map estimate, maximum a posteriori probability estimates. Now why is it called a map estimate? Do you know what mode of a distribution is? The mode of a distribution is the point at which the density function vanishes, the derivative of the density function vanishes, or density function peaks, assuming that it is a unimodal distribution. That is why you are looking at the point at which the density function is maximum. That is why it is called a map estimate. Okay. So now let us take an example of doing this. Okay, so before we do this, there is an idea called conjugate prior that I should talk about. See, we will have to incorporate our belief into the system, right. So remember that the choice of p theta is user defined, in the sense that we are free to choose whatever p theta that we want on the parameters. Now in the literature it has been suggested that we always choose our prior such that it is a conjugate prior. Now what do you mean by a conjugate prior? The prior on theta that ensures the posterior to have the same distribution, same distributional form as itself. So you choose a prior this way, you should choose a prior that would ensure that the posterior also has the same distributional form as itself. Why is this important? Think about it. Now let's take the example of this Bernoulli random variable that we are looking at. Now the belief that you have is that this the parameter peaks at 0.5 or whatever. Now having observed data, this should not transform into a Gaussian distribution, no? Why is that? See, remember what this distribution is over. This distribution is over the parameter of the Bernoulli random variable. The parameter of the Bernoulli random variable is bounded between 0 and 1. Now, just because you observed some data points which are the trials of that distribution, this parameter cannot suddenly have infinite support. Do you understand? Only the shape of this distribution can change. The parametric form cannot change. You see that? Right. So, that is why you need your prior to be chosen in such a way that after seeing the data, it should not change the characteristics of the prior. Mathematically speaking, the distributional form of the prior should not change after you observe the data. Does it make sense? Okay. So, that's what such a kind of a prior is called conjugate prior. Always choose your prior, incorporate your belief in this conjugate prior such that the posterior would not change the form of the prior.
The data is very different from our belief.
No. See, again, that's what I am saying. Data, okay, so belief is on parameters. Data comes from the repeated experiments. Now, just because you are doing the experiments, the underlying parameters should not change. You know, the form of the parameter distribution on parameters should not change. That's why I gave you this example. If you are conducting a coin toss experiment, after seeing data, the coin toss will not become a roll of die. That is what I am saying. It will still remain the coin toss. That's what conjugate prior is. Okay.
Unlike the latent variable and the data variable, random variable, this does not map to the sample space we are looking at, and it's kind of artificial.
Which one?
The parametric.
The distribution. Okay. The question is, does the paraphrase the question is very difficult. Okay, so the question is the following, that the distribution on the parameter space has nothing to do with the random experiment that is generating our data samples. That's correct. So there is another random experiment, okay, that is giving you the parameters. So basically there is a random experiment that gives you the parameters, conditioned on that you are generating data. That is what it is. Yeah, that's why you have p theta or px conditioned on theta, and you also have p theta conditioned on x. Okay, yeah, that's a good observation. Okay, let's look at now. Do you understand what conjugate prior is? Yeah, always choose a prior that would be conjugate. Okay, so let's look at the example. One example of a map estimate. So example of map estimate for Bernoulli random variable. Okay, let's look at, so now you have x, which is data that is sampled Bernoulli with parameters theta. There is only one parameter to estimate here, right? Bernoulli random variable will have only one parameter, okay, which is theta. We have, so what we have to do, first we have to construct the likelihood conditioned on the parameters. What is this? It's equal to theta power x times 1 minus theta times 1 minus x, correct? This is the distribution of a Bernoulli random variable. All of you with me? Yeah, okay. Now what is p theta? So now this is what we need to choose now. We have to choose the prior. What is the prior? So suppose you are looking at a Bernoulli random variable. What sort of a belief will incorporate, what sort of a belief is a reasonable belief on the parameters of a Bernoulli random variable? See, for one we know that it is bounded between 0 and 1, so we have to choose a distribution that is bounded between 0 and 1, okay, and what? That is the only constraint actually. What are the distributions that you know of that are bounded between 0 and 1? Uniform distribution is one, but is uniform distribution a good way to incorporate our belief? Because it is only saying that I know that all the values are equally likely. I mean, that is not what we need. In fact, if you take uniform distribution as your belief and construct a map estimate, it will be equivalent to an ML estimate, no? That can be shown actually, right? So uniform distribution is not something that we need. So what is the generalization of uniform distribution? It's the beta distribution. uniform distribution is a special case of these distribution functions called beta distributions that have bounded support. Okay, so beta distribution would be a good prior on this. So let us look at that beta distribution, and by the way, it also happens to be a conjugate distribution, conjugate prior, as we will see. So how do we write beta distribution? It is given by gamma plus beta divided by gamma times alpha into gamma times beta to theta raised to alpha minus 1 minus theta raised to beta minus 1. So this is the beta distribution where gamma is the gamma function, right, standard gamma function, and alpha and beta are parameters that we need to choose. So this is what our belief is, okay, our user defined or user chosen parameters. Okay, this is our belief. So now what should we do after this? So compute the posterior, which is p theta conditioned on x. This is what we need to now compute. So what is this equal to? We know that this is proportional to the condition prior times the conditional likelihood times the prior. Okay, so let us look at this. What is p x given theta? Just written that, no, 1 theta power x times 1 minus theta power 1 minus x. Multiply this with the beta distribution, which is I will again remove the constants, that gamma constant I will just remove. This is theta power alpha minus 1 times 1 minus theta power beta minus 1. Now this is a conjugate prior. Why? Now this will be theta power x plus alpha minus 1. Can you check the algebra? Is this correct? 1 minus theta times theta power beta minus x. Is this correct? Okay, so this is also a beta distribution, right? Of course, you need to adjust the constants to ensure that it integrates to 1. That can be done. So we are only writing it to proportional. So this is a beta distribution. That's why it's a conjugate prior. Now what happened with, we started with some initial belief on parameters theta. Now having seen data, our belief will change. So think about it mathematically. What do you mean by the belief of a belief over parameters changing in terms of distribution functions on theta? Here is the question. The question is, how do you incorporate your belief mathematically? It is by imposing a distribution on your parameters theta. Now having seen data, if I say that my belief has been upgraded and changed based on data, mathematically what would happen? The parameters that we have started with, okay, on the distribution of parameters will get updated, and that will become a function of data. That is exactly what is happening here, you see. Now you got a new beta distribution that has data in it, x in it, you see this. Of course we are doing this assuming that there is one data point. If there are n data points, there will be a sigma here, right? Because this p of x given theta will now be the product of, because we have made an ID assumption, right? There will be product of all of them. So you will have in the exponentiation, they will all get summed up. So you will have a sum of all these. Okay. So let us look at this. So now suppose, okay, so what do we do with this? Now we got a new beta distribution. but we want one single theta, right? Ultimately we want one value for the parameter that we use in our class conditional density or whatever to get the Bayesian get the base classifier or the optimal classifier estimated. Now what do we do with an entire distribution over theta? As I said, in map estimate you get the mode of this distribution, okay. So in map estimate theta map is taken to be the mode of the posterior theta given x, okay. So in the above case what is the mode of a beta distribution? It can be read off, okay. So given a beta distribution the mode can be found out, right. I mean it has an analytical form, I will just write that, okay. So you can, all you need to do is take the density function, take the derivative of it with respect to theta and put it to 0, you will get that. I will just write down the mode, it will be x minus x plus alpha minus 1 divided by alpha plus beta minus 2, this is the mode. Now this is for one data point, right. So suppose we have n data points, there will be a, and in the denominator you will have an n term. Now compare this with the ML estimate. What was the ML estimate? There is an xi here. So this was the ML estimate, okay. Now for n tending to infinity, what will happen? What would be the difference between ML estimate and map estimate? They will be the same. So that is the idea. So if you have infinite amount of data, then your belief does not matter. So that is why they say no. So one acquires a lot of maturity as one interacts more with the universe, right. So one should not be confined to one's room or whatever, right. So the more data points that you acquire, the better your estimates are going to be, all your belief will be erased off the moment you interact. See, look at this, right. So even with all the current day LLM models, belief does not matter because the amount of data that we look at. In fact, most of the ML that we do today in terms of LLM are ML estimates, because ultimately we will minimize the KL divergence and we get the ML estimates, as we will see later, okay. I already showed you, right, empirical risk minimization, ERM is an ML estimate. Now initially we had to incorporate a lot of belief in our model, etc., because data was less. Now if you have infinite amount of data, the ML estimate, the map estimate will converge to an ML estimate. So the belief will get erased. However, if you have small samples, then see, let us go back to the previous example, right. In the previous example, if all of them were 1, so this would have been 1, but now this is not 1. Why? Because you have the alphas and betas that would skew it to whatever the chosen belief was. Do you see this? So this is the map estimate. Now I mean some more examples will be done in the tutorial, but any distribution, okay, if the parameter of any standard distribution can be estimated in a map framework by choosing a conjugate pair. Okay, so any questions on this? Okay, see, there is, I will just state one thing, without going deeply into it. See, there are methods, this is just for your information, right. There are methods where instead of reading off one particular theta in terms of, let us say, mode or something and using it later, you can use the entire distribution on theta and carry the posterior belief further. What do I mean by that? Remember, ultimately, at least for this particular use case, we are interested in looking at the posterior of y given x, isn't it? And this we said was proportional to p of x given y, and this p of x given y is what we are estimating now. Okay, now this p of x given y is now a function of p of theta given x, isn't it? So you can carry this p of theta given x and get what is called as a full Bayesian estimate, where the final decision that you get on y also has uncertainty in it. See, in our base classifier, what happens is that you either choose class 1 or class 0 deterministically, but if you carry this uncertainty further, then even the final so called label that you get on y will incorporate that will also have that uncertainty, and p of y given x will again be another distribution, and that uncertainty is carried from p of theta given x. So given a particular theta, you will have this particular estimate on y. So it is like choosing a family of classifiers. If you choose one theta, you are choosing one model. Now if you have a distribution over theta, then instead of having one model, you are choosing a family of models. So those methods are called fully Bayesian methods. I will not go deeper into those methods, but I mean, yeah, so later in the course, right, when we look at neural networks, there are these kinds of neural networks that are called Bayesian neural networks. I don't know if you have heard the name of this. So they are these methods where the parameters of the model, in this case a neural network, is not fixed. So you have an entire distribution over the parameters of your model, and you carry the uncertainty all the way to the end of your decision. So that is the Bayesian framework of looking at the problem of risk minimization. So we will not go deeper into it, but yeah, so for now what we do is, once we get a distribution over theta, we choose one particular theta and use that for our model. That is our model. Remember, always in the parametric case of model building, theta is what we call as our model, right. So we get one model by choosing the mode. Okay.
This physics informed neural networks is there now. Can we look at them as map estimates?
Yeah, good question. The question is physics informed neural networks, which I have not talked about. Yeah, that's see, to me every architectural change that you do is a Bayesian estimate, right. CNN is a Bayesian estimate, right. A transformer is a Bayesian estimate. So any kind of incorporation, or rather restriction, that you do on the parameter space of any model is a Bayesian estimate, because what you are saying is, you are saying, look, my parameters should take a particular form. So later in the course, when I talk about fully connected neural networks and CNNs, I will show that a CNN is actually a Bayesian estimated form of a fully connected neural network, right. Yeah, so any architectural transformers are that way Bayesian estimates is my way of looking at things. I will talk about it later, okay. And this is also connected to the idea of regularization. We will discuss that in a couple of classes, from the empirical risk minimization viewpoint. We will stop here and continue in the next lecture.